All right, so now we're getting to the part that, well, I like. We're going to talk a little bit about repeated measures designs, and then we're going to talk about analysis of variance. And I'm going to try to keep it pretty brief. So basically, we've been talking about between groups designs. So within a one-way between groups design, each level of the independent variable is its own group. On the other hand, when we're doing a one-way repeated measures design, it's basically an extension of a paired design where participants are basically exposed to more than two conditions. So for example, this is based off of a study by Donahue looking at whether or not critical thinking training can change from pre-test to post-test, sort of like what we found with the Thomason study. And what's actually kind of interesting is that Donahue actually followed up with groups of college students 9 months later. So in this particular case, the independent variable is always going to be within groups. Everybody gets the pre-test, everybody gets the post-test, everybody gets the follow-up. So this is one example of what it might look like. Another way that we might look at this is if I vary set size to look at working memory performance, every person is getting exposed to all possible set sizes. So everybody is getting exposed to all experimental conditions. So Donahue basically tested 20 students on a California critical thinking skills test. All of the students were enrolled in a freshman critical thinking course where they had to map arguments. They did a pre-test, a post-test, and a 9-month follow-up. Remember that when we talk about a repeated measures design, focusing on the overlap is really not helpful at this point. And one of the things that we're also going to take into account is that here we need to draw a line. This can help us remember that we are looking at data from the same people every time and that they're not independent groups. So just like with our independent groups design, you are going to select the number of contrasts that you want to make in advance, and that needs to be your number of conditions minus 1. Calculate a mean and confidence interval for each planned contrast, and basically make sure you're reporting those as the main findings. You can explore further you can explore more contrasts if you wish, but note that they're exploratory and be tentative with them. We're not going to be doing any calculations for the one-way repeated measures design, and ESCI isn't really going to do that for you either. So what can we do instead? So without doing a calculation of any kind, focus on the comparison of the post-test and the follow-up. Notice that we're kind of staying at the same level. If you want to play around with data on other ESCI pages, this can give you a rough idea of what you could expect, but remember that you're looking at a repeated measure, so looking at things like overlap is not going to be helpful. I think what's probably really important to note here is that if you look at each individual data point, for the most part, most people are not decreasing from post-test to follow-up. We do have a couple of cases of people who make very severe decreases, but I'd say kind of look at the ratio of decrease versus increase and stayed the same. So we want to see that they have either maintained or increased that versus decreased that. And that can give you a pretty good idea of what's going on with the data. So what are our basic assumptions for a one-way repeated measure design? Again, data at each level of the independent variable are going to be a random sample from a population that's normally distributed. We've got our homogeneity of variance, and additionally, since this is within subjects or repeated measures, these should be pretty highly correlated with each other at every level of the independent variable. And in fact, Donahue and colleagues did find that this data, even at the follow-up, is very highly correlated. I believe it was about 0.8, and that's pretty good. That's a good sign. So now we're going to finish up with this, and they dislike ANOVA much more than me, and they basically say, I don't understand why people still do this. Well, I do. So one of the ways that we look at experimental designs that have more than one independent variable, or an independent variable with more than 3 or more levels, is with what is referred to as an analysis of variance, or an ANOVA. So one of the things that I would mention that your book does not, part of the reason that we like analysis of variance, why people who do null hypothesis testing like it, is that it's what's known as an omnibus test. So basically, the very first thing that you're going to do is see if there is any difference of any kind between your conditions. And then only if we find a difference between those conditions, then we're going to look at different contrasts. And I think that that is really useful. If you are new to doing data analysis, if you are new to doing statistics, and you don't really have an intuition for what kind of contrasts you should be doing, I think ANOVA is a great way to start. I don't think once you gain more knowledge that it's the only thing that you should be doing. But I think if you're new to the game, it can be very useful. I'm going backwards. Okay, so ANOVA is absolutely null hypothesis testing. Now, despite the fact that your textbook authors note the advantages of this, ANOVA does tend to dominate, and so you need to understand at least a very basic idea of how it works. And I would say you can do planned contrasts with ANOVA. You can also do post hoc contrasts. What I actually like about that is that you do take a statistical penalty of sorts for those post hoc contrasts. And you're only allowed to look at contrasts if you find that there is an effect of some kind going on in your variables. So, and yeah, I'm a little biased. I'm Team ANOVA. Like I said, I grew up with ANOVA. I've been doing ANOVA since graduate school. I teach ANOVA, so I'm a little biased towards it. I can see more benefits than they do, but I also see the disadvantages for what they are. So basically, what does ANOVA specify? So when we talked about things like t-tests and null hypothesis testing, what is our null hypothesis if we're looking at ANOVA? The basic null hypothesis is that all group population means are the same, that there's no difference. So if even one mean is different from the other means, you have to reject the null. That's kind of nice. So this independent variable is what is referred to as factor A. And when you're doing an analysis of variance, the critical statistic is F. F needs to be sufficiently large for a p-value to be sufficiently small. The larger your F is, the better. If your F is 1 or less than 1, you do not have significance. And here's why. Now, I'm giving you the Cliff's Notes version. I do not expect you to do this or calculate this on your own. Informally. Now, technically, the F statistic is made up of what we call our mean squares between over our mean squares within. Now, what does that mean? It's basically put like this. The variability between groups or conditions needs to be larger than the variability of the data within a group pooled over all groups. So we need to see more between groups differences than we need to see within groups. So the larger this is, the more that we can be sure that the variability that we are seeing is due to our conditions or our manipulations and less due to chance or randomness or the fact that people are just different from each other. So in a journal article, you might actually end up reading something like this. The main type of feedback was statistically significant with an F. So we have 2 degrees of freedom here. So we have the degrees of freedom between. So that's basically your number of independent variables minus 1. So in the case of feedback, we have those 3 different types of feedback. So it's our levels minus 1. And then we have 38. And so that is what is called our degrees of freedom within. So this is our numerator degrees of freedom, our denominator degrees of freedom. That is an F statistic. An F of 4 is pretty good, and it has a p-value of 0.02. So if you are looking at an F statistic, you will always see a degrees of freedom with between, which is your numerator, and degrees of freedom within, which is your denominator. So if we are doing a repeated measures design, the null hypothesis for an ANOVA is basically the same. Now, what makes a repeated measures ANOVA more complicated is that we are now partitioning some of the variability that we see between conditions. We are partitioning some of that to a person. So F is still going to be a ratio of the effect between conditions versus within a condition, but it's more complicated because we also have to take into account that each of these conditions is being done over one person, and we actually have to partition out that variability. Because of that, the design is going to be more sensitive, and the assumptions are going to be the same for contrast analysis. Now, one thing that I think is really cool that your book mentions, and I think it's actually a benefit of ANOVA compared to just doing pairwise contrasts. So if we get a significant effect of some kind in an ANOVA, you then get post hoc contrasts. Now, these post hoc contrasts are exploratory, but your book does note that they do actually adjust the p-value downward because it is post hoc. So it basically does have a couple of levels of protection. So a post hoc contrast is declared statistically significant only after we actually have a significant effect of some kind. So you can't do a contrast if there's no significant effect. Additionally, it's going to take a harsher p-value because you have to take a statistical penalty due to it being post hoc. And that's actually kind of nice. If you don't know or have a very good understanding that the more contrasts you do, the greater statistical penalty you have to take, something like ANOVA can actually be really useful because it does all the hard work for you. And that's just what I think. Now, in terms of reporting your work, you need to indicate whether or not the contrast is planned or exploratory, unless you've made that clear. You need your basic descriptive statistics. That will be the group difference or the effect size of interest and its confidence interval. You may want a standardized effect size estimate that's not done biased, it's D unbiased, with its confidence interval on Cohen's D. You like figures, please use them. If you want to use an ANOVA, go ahead. If you want, you can include that. That will include an F statistic, degrees of freedom, an associated p-value. For those who like it, some standard effect size measures for ANOVA include eta squared, partial eta squared, and something called omega squared. I tend to use partial eta squared. If you ever have questions, you can ask me. I can show you how to calculate it. Additionally, you need to make an interpretation of the group difference that considers not only the point estimate, but also your confidence interval on the difference. So y'all, you did it. You made it to the end of the semester, and now that you are done listening to me, you can complete your Chapter 14 handout. Again, really quick, just to kind of show you where you need to go. I would say go to the comparisons page. I suppose if you want to do a subset contrast, you can. You would want to do a subset contrast if you want to look at generic versus brand name. You could do a subset contrast for that. You are also more than welcome to just do a comparison. And remember that you need to pick two. You need to pick two, and you don't have to pick the same two as everybody else. So it's whatever is more interesting to you. I want to open this up to you really quick just so you can see where you can enter in the data or copy and paste the data really quick. Excel is taking its sweet time to load while we wait. And the cat is coming over to wish you a wonderful holiday season. Come here, Earl. Come here. Okay. So again, just to kind of show you where you will want to go, if you want to do a comparison, so if you want to compare generic versus Hershey's, or generic versus Godiva, or Hershey's versus Godiva, in this case, you are going to do the independent groups comparison page. If you go to full data, you can actually copy and paste that data into this. So it says full data, and then you would want to make sure that you have the names for all of those in your summary statistics. Now, if you, for example, want to compare generic chocolate versus brand name chocolate, you would want to lump Hershey's and Godiva together, and you would want to do a contrast. And again, you can enter in that full data in the data entry options, click the radio button that says full data below, and copy and paste that data in. So if you're having trouble with this, shoot me an email. Hopefully kind of going over this on Esky with you will help you feel a little bit more comfortable messing around with this. I had a wonderful semester with you, and it's not over yet. I will see you at the next Sunday night study session if anybody shows up. But that is it for lecturing, and I will see you very soon. Bye, everybody.